Good evening, everybody. Today is a very wet day, and I think we're very encouraged by such a good turnout for this public lecture. And I can assure you that you'll be very much rewarded for coming. As I just talked to Professor Markowich, you're going to see more than you hear in today's public lecture. Am I right? Well, this is one of the public lectures organized by the Institute for Medical Sciences at NUS. As you probably by now are aware that we have from time to time we organize public lectures by inviting distinguished institute to share their experience and knowledge with the general public, knowledge of mathematics and its application with the general public. We are very happy and to have Professor Peter Markowich as our speaker tonight. Professor Markowich works in the area of partial differential equations and their applications in science engineering. He holds a chair in applied mathematics at the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. He is also a professor at the University of Vienna and leader of a research group at the Johann Radon Institute for Computational and Applied Mathematics in Linz. He was a recipient of the Austrian Wittgenstein Award in 2000 and of the Boltzmann Research Merit Award of the Royal Society in 2007. He was also elected as a corresponding member of the Austrian Academy of Sciences in 2005. So it is now my great pleasure to invite Professor Markowich to deliver or to show his public lecture.
Well, thank you, Luis. It's really a great pleasure being here. It's far away from where I live and work, but I mean the turnout really makes it worthwhile to come here. And I'm very grateful to the IMS, in particular to Luis Chen and Wei Bao, who is organizing this beautiful conference on Rossby-Zajewski equation and Bose-Einstein condensation, for having me over. It's really nice to be here. Thanks for coming. Okay, let me first, maybe we could turn off the light. Let me first say a few words on the overall setup of this lecture. Well, first of all, as Luis already said, you're going to see maybe more than what you will hear. The reason is that I'm going to show you photographs. Many photographs and my own photographs. And one reason why I show you these photographs is, of course, hopefully for your enjoyment, because I think they are nice photographs. But more importantly, behind every photograph there is a scientific story, in the sense of that I will use the photographs to illustrate phenomena which happen in the nature around us, which happen in technology, which happen in sociological processes, to illustrate that there is mathematics, complicated mathematics, and in particular mathematics of partial differential equations, which can be used to solve or to tackle and hopefully solve these problems. So this is more or less the setup, so be prepared for an onslaught of pictures. Partial differential equations. Well, what are partial differential equations? Well, first of all, they are equations which relate physical state variables like mass, velocity, energy, to their variations with respect to so-called independent variables, which could be space or time, for example. Partial differential equations, or as I shall call them, PDEs, have a really long history. They are based on differential integral calculus as invented by Leibniz and Newton in the 18th century. And I think since then they have had a very big success story They were used by very important scientists to solve very important problems. For example, they were used by Euler, Maxwell, Boltzmann, Navier, Stokes, Einstein, Brandt, Schrödinger, Pauli, Dirac, Turing, and recently also by Black and Scholes in finance mathematics. And PDEs actually provide an important modeling tool for the physical sciences, for theoretical chemistry, for biology, for the socio-economic sciences, and for the engineering sciences. And finally, and actually last but not least, I should say, PDEs are very nice from a scientific point of view because they are accessible to numerical simulations, and in this sense they are accessible to practical exploitation. Well, PDEs, as you will see, PDEs govern many phenomena which occur in the nature around us and in the socio-economic behavior of human populations. They are indispensable for advancing engineering technology. And finally, and also last but not least, I should say, they involve deep and beautiful mathematics. Now, the topics which I shall show you in the next hour or so, well, they range over quite a wide, well, they vary over quite a wide range. So I shall speak about gas dynamics, gas kinetics, in particular the Boltzmann equation. Then move on to fluid and gas dynamics, now the Stokes-Euler equations, of course. Then I'll talk about kinetic modeling of granular flows. Then move over to mathematical biology, in particular chemotaxis and formation of biological patterns. Then technology, semiconductor modeling, of course, is important for all of us. We use computers on a daily basis. Then I'll speak about free boundary problems and interfaces, reaction diffusion equations, on the Mosh-Kantorovich optimal transportation problem, wave equations, digital image processing, and socio-economic modeling. Well, I mean, you could ask, of course, the question, why this selection of topics? But the reason is very simple. It is problems I have scientific experience with. So, I mean, the choice is very personal and, of course, very biased, and by no means exhaustive. I mean, you could continue this list on for a very long time, but then the lecture would probably take for a week. So I move on. Okay, let me get into gas kinetics immediately. Well, what you see here is a formation of clouds. To be more precise, as the specialist told me, it's a formation of altocumulus lenticularis duplicatis, which you see over the plains of Patagonia. Patagonia is a stretch of, it's basically the most southern tip of the American continent, shared between Argentina and Chile. Well, I mean clouds, right? Clouds belong to the atmospheric system, and as such, they are at least partially controlled by gas kinetics. So what's the mathematics behind gas kinetics? Unfortunately, these are very big files, so it takes a while. Well, in gas kinetics, basically we are interested in the so-called phase-space density. You can think of it as the probabilistic phase-space density of the particles of the gas. Phase-space meaning that as independent variables we have the position variable and the velocity variable. And of course you can think of time as a parameter which evolves. And here I'm interested in the motion of the gas under the influence of an external force field. You can think of, for example, think of the wind which blows at the cloud. Well, then there is the so-called Boltzmann equation of gas kinetics, which is for sure the most fundamental equation in this field. And actually it's called Boltzmann equation, although I should say that it was not written down by Ludwig Boltzmann for the first time. Actually it was James Clerk Maxwell who wrote it for the first time. And Boltzmann then later on had some very important insights into it, particularly in particular as far as entropy is concerned. So basically what you see is, well, the left-hand side of the equation models the streaming of the particles. Here's the free streaming operator, and here's the streaming induced by the force field. And the right-hand side is a complicated, non-local integral operator, quadratically nonlinear. And this models the binary collisions of the gas atoms. So basically you have to think of, when you see the Boltzmann equation, you have to think of a dynamic balance of convection, free streaming, and collisional effects in the gas. Now, a very important application of this lies in the microphysics of clouds. But basically you have to think of clouds as consisting of air, of course, of vapor, and of ice. And basically, basically water droplets. So basically what we're interested in is the probability distribution of the drop mass density. So basically what happens is drops of water can coalesce, they can separate, and you're interested in how, in the statistics of the drops of a certain mass. And this equation, which is obtained from the Boltzmann equation, actually is called the stochastic coalescence equation. And here I've written down the homogeneous, that means space-independent version of it. And what you see here is on the right-hand side an operator which sort of resembles this nonlinear, quadratically nonlinear, non-local Boltzmann operator. So this governs the microphysics of clouds. Well, there is another application, of course. This is macroscopic cloud modeling. Basically, macroscopic cloud modeling, meaning here we are discussing distances which could range over kilometers or tenths of kilometers. Very often people use lattice Boltzmann equations. What are lattice Boltzmann equations? Well, basically, they are space discretized versions of discrete velocity collisional kinetic equations. It has been shown that there is convergence to solutions of the Navier-Stokes fluid dynamics equation in certain scaling limits. And lattice Boltzmann equations can actually describe clouds, wind, smoke, and other kinetics. And they can represent complicated geometries, for example, and also phase transitions and chemical reactions, and so on. Now, of course, there is another way of modeling clouds in a macroscopic way, and this is done by fluid equations, essentially Navier-Stokes equations. And here the important thing is the interaction of air with cloud particles, like water droplets, ice crystals, or other particles. And this has to be done, of course, on a microscopic basis. Well, there's a big difficulty involved here, which is the vapor-water droplet formation phase transition. This is really a very hard problem for cloud physics. Well, what you see here is a huge, so here we are really talking macroscopic cloud dynamics. Here what you see here is a big cloud approaching the volcano Cotopaxi in Ecuador. You have to think of the Cotopaxi has altitude something like 5,800 meters, so you can think of how big this cloud really is. And here you see the cloud being convected towards the mountain. So basically this would be a classical case for either macroscopic fluid dynamics or lattice Boltzmann model. What you see here is two different kinds of clouds. You see here high up the so-called cirrus flocus clouds, and low so-called cumulus clouds over the actually Cuernos del Paine, again in Patagonia. And what you see here is very complicated patterns of clouds. And what is interesting is that people who work in computer vision and who program computer games, very often they are in the position of having to generate such complicated cloud patterns or smoke patterns. And very often they use lattice Boltzmann simulations because they are very fast and they can do them in real time. You see that complicated mathematics has even entered the field of computer games and computer vision. But actually here you see a very complicated cloud pattern. Cumulus clouds over the Torres del Paine. Yeah? So you can think of that generating such patterns in a computer game is really a major job. Now, other applications of gas kinetics, of course, in aircraft or in spacecraft design. Now, when you think of the problem of the space shuttle re-entering into the atmosphere, basically this is very nice because in some sense you cover all the three different regimes of kinetics. Well, you have a ballistic flight in outer space. So in outer space, the shuttle basically moves under its own force. Nothing happens to it. Then, as soon as the shuttle enters into the upper atmosphere, you will have a dynamic balance of collisions of the shuttle hull with air particles. And when the shuttle gets finally lower, you will have some very small mean free path flow in the lower atmosphere. So you will be in the fluid regime then. So basically what it means is that you have a transition from collisionless ballistic flow to collisional kinetic Boltzmann flow to essentially macroscopic fluid dynamics. If you want to describe the complete re-entry phase of the space shuttle. And actually this has been done by NASA as well as by the European Space Agency. In fact, something like 15 years ago when they were still interested in constructing the European space shuttle. Now, of course, a very important problem is aircraft design. In particular, the design of the wing is a very subtle issue. And this is actually a typical task for experimental and computational fluid dynamics. And people in general use incompressible Euler and Navier-Stokes equations, or actually compressible models, compressible versions of these equations, depending on essentially the speed of the aircraft under consideration. Actually, also lattice Boltzmann simulations have been employed recently for the design of airfoils, particularly in the case of turbulence modeling. So here you see an aircraft, a plane, departing from the city airport in Rio de Janeiro. So here we are facing a low altitude flight, and here the modeling would certainly be incompressible due to the fact that the plane is also not moving very fast yet. Well, finally, in this part of the lecture, I'd like to show you the bust of the man who began with it all, the man, as Judge Miani says, who believed in atoms, Ludwig Boltzmann, at his grave in the Central Cemetery of Vienna. And what you see here is the entropy formula. This is really what's about make Boltzmann very effective. Okay, now let's move from gas kinetics to fluid dynamics. So what you see here is a photograph of the famous Iguazu Falls, which you can find somewhere in South America on the border between Brazil and Argentina. They're really very impressive falls, and they have very complicated topology and so on. But here, let me just say, there's just one case of fluid flows. And fluids are, of course, all around us, and flows of fluids have occupied scientists for centuries. And, of course, the mathematics of fluid flows is highly developed by now, although I should say not completely under control yet. Now, what are the equations? Well, in some sense, the most basic equation for fluid flow is the compressible Navier-Stokes system, which you see here. So basically what we have is the momentum balance of a small fluid system. The unknowns here are the three-dimensional velocity field U and the pressure P. So you have to think of here the convection term, you have to think of the force field due to pressure gradients. Here you have to think of the kinematic viscosity term, and F is an external force acting on the fluid. I shall show you an example in a moment. And then you have the condition for incompressibility, which means that the divergence convergence of the velocity field of the fluid is equal to 0. Now, if you want to get rich, you just have to solve a very important problem connected to this system of equation. All you have to do is to show under reasonable mathematical hypotheses, which are specified by the Clay Prize announcement. You have to show that there are global, in time, smooth solutions of this problem. Now, yeah, you can win $1 million. If there were no globally defined smooth solutions, this problem, in my view, this would sort of change, or we would have to change the way that in which we look at the flow of fluids. When we think of fluids and flows, we always think of smooth velocity fields, at least smooth to some degree. In any case, this is mathematically an unsolved problem, and everybody is, of course, highly welcome. Many people have. Not enough to buy a house in Singapore, but at least you can start. Well, a very important application, hydrology. Let me get back to the waterfall. So basically, hydrology, we're interested in the flow of rivers, flow of rivers in waterfalls. We're interested in dams, in the breaking of dams, and so on. And an important system which is basically derived out of the Navier-Stokes system is the so-called Salvenant system. The Salvenant system is essentially, well, the unknowns is this function h, which is the water height over bottom of the river, for example. And then you have the velocity field u, which here is 1 or 2 dimensional, because we assume that there is no flow in the third direction. Yeah? And the system that comes up looks like a compressible P system with a quadratic pressure law. And external forcing, and you see the external forcing is done by the gradient of the bottom topography. Yeah, so this is really the system that you can use to model waterfalls. And here you see another photograph of these falls, and you see that there's very, very complicated topography. But I should say that people really have used the Salvenant system to model complicated situations like this. Well, here you see already, I shall get back to that in a moment, you see different types of flows. You see this very rapid, you could say turbulent flow, and I shall specify that later on. And here you have some slower, almost laminar streamline flow. And of course there's a transition regime. Well, here this is a very fast-flowing waterfall in South Africa, actually. And basically what you see here is, I mean, you see this water coming down, being very wide. This is essentially because air is resolved in it. So if you want to model this accurately, you would have to look at a two-phase flow problem. You have gas bubbles in it. They're very complicated. Well, turbulence. I said turbulence. What do we mean by turbulence modeling? Well, turbulent flows are characterized by apparently chaotic random changes of the velocity. And you have vortices which appear on a variety of scales. And this typically occurs at large Reynolds numbers. Non-turbulent flows, as I already said, are called laminar. They are essentially smooth, nice flows along streamlines, and characterized by the fact that different layers of the flow, of the fluid, are not disturbed by the interaction of scales. Of course, simulations of turbulent flows are highly complicated and very expensive, because you cannot just solve the problem on one scale or on two scales. You have to go from a very large scale and you have to couple it all the way through down to the small scale. But there have been simplifying attempts which are called turbulence modeling in the literature, and they are essentially based on very complicated time averaging of the Navier-Stokes equations and using empirical, more or less empirical closures. In some sense, very close to what we do in kinetic theory. Let me show you an instance of the turbulent flow. This is very classical turbulent flow, basically, you have to think of this as tenths of meters, so you have the large scale, then you can see all the way when you go down, there's a lot of microscales in this fluid, yeah? And of course, when the water keeps flowing, the behavior seems on the microscale, even seems to be quite random. Now here you have a typical situation of a transition between extremely turbulent flow up here and more or less laminar flow down there, and here you see the transition region. Okay, now I talked about fluids, let me say a few words on granular material flows. Well, a classical granular material is of course sand, and what you see here is wind ripples in a sand dune, which is actually in Sossusvlei in the southern part of Africa. So, how do we model granular flows, granular materials? Well, first of all, they are characterized by the fact that they consist of small grains. And their kinetics, their motion, is driven by essentially binary collisions of grains. But contrary to what we are used to in gas kinetics, collisions of granular material basically dissipate energy. So you can essentially write down a Boltzmann, or actually it's called Boltzmann-Ainskopf equation, but you have to keep in mind that the collisions which govern the flow are inelastic, they lose energy. So basically the equation looks very similar to the Boltzmann equation which I've already shown you. There is the particle convection term on the left-hand side, and here you have the right-hand side again, an integral operator, binary collision, so you have reductive nonlinearity, but here you have this factor chi up front which is responsible for the loss of energy in the collisional process. Now actually from this kinetic model you can write down macroscopic scaling limits. That means you can formulate the system in terms of the particle, the density rho, the velocity and the temperature. When you do this you find a system of equations which looks like the compressible Euler equations for fluid, except one big issue, you have this temperature relaxation term on the right hand side. Now how can you realize this? Well, the next time you walk on a sand, you just put your foot into the sand. And what you will realize is that suddenly your foot gets very hot. And then, after a while, there is relaxation of the temperature. And the heat which you feel is precisely generated by the collisions, by the inelastic collisions of the grains of sand which the motion of your foot causes. And then the dissipation is actually described by this minus sign here. Now, granular materials arranged in very peculiar shapes. So what you see here is the so-called dune 45, again in Sossusvlei. Of course, this arrangement of the material is a stable one. One of the many stable ones, actually, I should say, is here. If you take a glass of water and you shake it, and then stop shaking it, you will see that it relaxes to the unique steady state. Well, in a granular material, this is completely different. Granular materials can assume many different steady states. So basically it means they have a very complicated energy landscape. Well, here you see one steady state, which is this dune with this complicated formation of the ridge, which of course comes about by essentially interaction with the environment, wind and so on. So here, in order to model the shape of the dune, which people have actually done, we have to go, of course, into macroscopic physics of granular materials. So you see that dunes can really have very strange shapes. You see here this so-called Bacher dune, which essentially is a ring, but has one opening. And people have really modeled these shapes mathematically by using PD. So here you see a classical shape of a ridge of a dune. Yeah? And actually the physics of the shapes of dunes is really also covered by the microscopic collisions of the sand particles. And basically the motion is caused by the wind which blows on the dune and moves the sand particles, and then they start to hop around. This is called aeolian transport. Here you see very complicated steady state in this dune field in very peculiar shapes. Well, here you see dunes, what I call the blue hour, in that value. Well, as I said, granular materials can assume many steady states, and they all are stable in some sense. So what you see here is one of these stable configurations are basically called wind ripples, again caused by bilateral winds blowing on the dune. And here you see that a Zen artist has made use of the fact that there is many steady states of granular materials. This is a piece of artwork in a Zen garden in Kyoto consisting of very small pebbles. Well, when you see piles of granular material, of course you ask the question, why is this pile stable? And actually when you go into the mathematics of piles, of the formation, growth, collapse, stability of piles of granular material, basically you have to check out Mosh-Kantorowicz mass transportation theory, which I shall discuss later on, hopefully. Basically you end up with P Laplace equations, which you have to study. Okay, let's go into biology. In particular, let me say a few words about chemotaxis cell motion and biological pattern formation. So what you see here is a photograph of a zebra head. And of course you see the very famous zebra fur pattern. So it's one of the main questions of evolutionary biology. Why do these patterns exist? How are they generated? And what's the mathematics behind it? Well, very related to this problem is the problem of motion of biological cells. And actually one main mechanism why cells move is given, or how they move is given by so-called chemotaxis. Chemotaxis is basically the motion of biological cells driven by a chemical, and usually this chemical is self-produced by the cells. So you can think of, for example, a swarm of bacteria which tries to move towards nutrition, somewhere say an organism, and the bacteria then generate a chemical which tells their pals where they should move to. And this process is called chemotaxis. Actually, it's a very similar process to processes which happen in embryology, immunology, and so on. And the mathematics is actually a system of reaction diffusion equations called the so-called, or one mathematical model, I should say, called the Keller-Segal model. And the Keller-Segal model is consists of one partial differential equations of, Fokker-Planck type for the cell density, R, coupled to an equation for the chemical concentration. And you see here the reaction term depends on the cell density itself, and this is what I said. This reflects the fact that the bacteria or the cells generate the chemical. And there is also a possibility for destruction of the chemical involved. So this is the famous Keller-Segal model. Back to the pattern formation problem. Well, the main idea for the mathematical modeling came from Turing, British mathematician Alan Turing. His idea was basically to write down a reaction diffusion system consisting of, say, two equations, and he called one substance the activator, and he called the other substance the deactivator. So U and V you have to think of as concentrations. And the idea is that you can write such systems which have the following feature. In the case where there is no diffusion, assume you have a stationary state which says 0, 0, and this stationary state is stable. Assume you have such a situation, very easy to generate. then you can prove that if you add diffusion in both components with diffusion coefficient, or with a diffusion coefficient b here, which is significantly different from 1, then you can generate a situation where this system is unstable situation. And this instability is precisely what, or actually these unstable modes are precisely what causes the pattern formation. This was Turing's idea, and actually recently has been proven in a way that activators and deactivators can be chemically identified in certain organisms. So it's really a fascinating mathematical effect, because typically when you think of diffusion, you think of the fact that diffusion stabilizes a process. And here it's exactly the other way around. If you have significantly different diffusions, the process is becoming destabilized. The analysis of this is actually really simple. Fourier analysis, essentially. Well, what you see here is of course a giraffe fur pattern, and it's interesting to see that people have really generated these fur patterns by solving Turing systems of the kind of that I've shown you. So you can actually model these very accurately by reaction diffusion system. Well, the same with simpler Kubus patterns and zebra patterns, of course. Right? So actually people have, here again, people in computer vision who are in some sense on the forefront of computational needs, because it all has to be very fast. They really generate zebra patterns by solving Turing-type PDEs, of course, in a very simplified framework. Zebra code pattern again here. Crocodiles, precisely the same. You see these very complicated skin patterns, which are, as Turing claims, supported by this instability in the Turing system. But here you see a turtle in Galapagos Islands, actually a turtle is trying to find its way. What is remarkable about turtles is, of course, the shell. And there's been a big discussion in biology, how is the shell generated? And actually now people have found out that chemotaxis is the main mechanism of generating the shell in turtles. Again, modeled by the Keller-Siegel system. Okay, let me move away from biology, let me move into technology. We all deal with semiconductors, of course, on a daily basis in the computer, but basically what you see here is just one example. You see a chip. Actually, this is an ATA controller chip, disk drive controller. But in this chip, there is many semiconductor devices. You can think of millions of them. Yeah? The question is, of course, how are semiconductor devices modeled? Well, again, it's PDEs. And the main modeling of semiconductors is based on what we call now the drift diffusion system for semiconductor devices. Basically, in semiconductors, you have to think of that you have two types of carriers. You have positively charged carriers, which are called holes. You have negatively charged carriers, electrons. And you describe by a reaction diffusion system, you describe the motion of both, or the current flow of both. And the driving force, of course, is the gradient of the electrostatic potential, and the potential is generated by a Poisson equation. Essentially, this system can be derived from the Maxwell equations plus some additional constitutive assumptions. Actually, this system is pretty old now. It was written down in the 60s. Yeah, it was written down in the 60s. And up to now, modeling of semiconductor devices is to a large extent done by using various versions of this system. Of course, when you have chips, you have to think of something different. For example, what you see here is the motherboard of a computer. Here are the two slots for the processors. Again, each of the processors consists of millions of semiconductor devices, and when you model a VLSI structure, what you basically have to do is you have to assemble the output of the individual semiconductor device models. And basically what you get is a big system of ordinary differential equations for the whole, for the output of the chip, which has to be solved. But here again, here you have a processor, actually pretty old technology. By now, consisting of silicon, essentially a silicon wafer, and in there you have millions of semiconductor devices. And precisely the same in a RAM array. Yeah? Also, well, RAM cells basically consist of RMOS, metal oxide semiconductor devices, main modeling done by drift diffusion systems, even in the most sophisticated semiconductor designs of today. Chipsets on the graphic card, precisely the same. So you see that PDE technology has really entered the realm of computer technology as we know it today. Okay, let me move back into nature. Let me say a few words about phase transitions and free boundary problems. Well, what you see here is an iceberg in somewhere again in southern Patagonia, and basically, when you think of icebergs, there's two very complicated problems to be solved. Well, one is the modeling of the part of the iceberg above water, and the other problem is the modeling underwater. Of course, both problems are completely different. Why? Well, because underwater you have a phase transition of the same material, water ice. And the shape and the geometry of the iceberg underwater is governed precisely by this phase transition. Over water, well, there is a lot of effects which enter, which is solar radiation, ablation, and wind, and so on. Now, both these problems are free boundary problems. What is a free boundary problem? Let me say a few words about the most simple free boundary problem that you can think of, which is the so-called obstacle problem. What's the obstacle problem? Think of a two-dimensional membrane which you want to move over an obstacle, which could be a rock. And assume that you clamp this membrane on its boundary. So basically what will happen is, if you move it sufficiently low, there will be a part of the rock which coincides with the membrane. Then there will be a part of the membrane which does not coincide with the rock. And of course there will be the interface, which is the boundary of these regions. This is called the free boundary of the problem. So how is this modeled mathematically? Well, basically the membrane tries to minimize its energy. And the energy is just given by this expression here, where you can think of V as the displacement, as the local displacement of the membrane. Now minimize the energy, well, over which set? Well, you have to have a set which incorporates the obstacle. So basically you can only allow test functions which are larger or equal than the obstacle. Now when you minimize this functional over this set, it's actually an easy exercise to show that can be done. Basically what you know, well, what you get as a solution of the problem is two pieces of information. You obtain the minimizer itself, which is the minimal, which is the displacement of the membrane as a function of position, and you also obtain the free boundary. So free boundary problems give two pieces of information, a function and a geometric information, a set, called free boundary. Now, this is the most simple obstacle problem. When you think of iceberg modeling, of course the situation is much more complicated, but the model, well, the model is in some sense similar. It's called the single-phase Stefan model, written down by the Austrian Slovenian physicist Stefan, and he was really interested in the evolution or in the growth of icebergs in the Arctic. So this is really how this problem came about. And basically what you model is the temperature, just for normalization, the negative temperature in the solid phase, and then you are interested in the location of the phase transition. This is the free boundary. Basically you write a heat equation for the temperature in the solid phase, Well, this heat, as I said, holds only in the solid phase, temperature is fixed in the water, of course, and then you need to determine this free boundary. And for this, basically, what you need to do is over-determine the problem. Yeah, so you need an additional condition, which is the so-called Stefan condition. L is a latent heat parameter. And then basically you can solve it. And this problem governs at least a one-dimensional version of the growth of icebergs underwater. And there is a corresponding 2D and 3D version. And so on. Now here you see a layer, what's actually called a layered iceberg, and this is, well, essentially what you see here is you see the intersection of the fixed boundary with the Stefan boundary. You don't see the Stefan boundary itself because it's underwater. But basically what you face here is the problem of describing the shape of the iceberg overwater. Again, this leads to a free boundary problem, but a much more complicated one because you have a lot of collateral effects. And you see that actually free boundary problems can be geometries with very peculiar shapes. Or here you see a melting iceberg. Well, of course, melting is one of the main features which creates the shape of the part over water, and which has to be taken into account in the model. And here you get a glimpse of the Stefan boundary, which is the boundary underwater, right? So you see this would be essentially the three-dimensional Stefan boundary of the iceberg. Now you see that actually boundary value problems can have a very complicated solution structure. In particular, you can have a very complicated geometry of the free boundary and of course of its intersection with the fixed boundary. It can become very fractal. Well, another example for free boundary problem, or where free boundary problems become very important, is in the modeling of the flow of glaciers. What you see here is essentially a glacier flowing into the Lago Argentino, again in Patagonia. And the question is, how do we model glaciers? Well, you have to go into the physics first, and then, well, glacier is basically flowing ice, so you're kind of bound to fluid equation. Now then you have to take into account the fact that the flow of glaciers is slow and of course incompressible. Then you have to think of the constitutive relation between the ice strain tensor and the viscosity. This is the main part of the modeling actually. And this then leads to what is called the classical model of glaciology, which is a time-dependent version of the obstacle problem, and the solution is the local glacier height. And what is the free boundary? Well, yeah, first of all, what is the obstacle? Of course, the ground topography. The glacier flows over ground, which has a certain geometry. The free boundary is, of course, the edge of the glacier. And then you have to consider reaction based on snowfall, and of course, ablation by solar rays. And this model can then be written down in a rather straightforward way. And then you see that actually solutions can be very peculiar. You can have these classical shapes of penitents. They are called penitents because they resemble a procession of Catholic monks walking towards a church or something. So you see that free boundary problems can have complicated solutions. And here you see the edge of the glacier, which then is really the free boundary, the solution, the second piece of information of the solution of the free boundary problem, that is the geometric piece. Okay, and then here you see a glacier front entering into a lake, and what you see here is basically highly compressed ice, so which sort of contradicts what I said before. There is apparently a density variation in the glacier, but in the typical model this is negative. Okay, let's go into warmer climates. Let me say a few words about biological environments, homogeneous and heterogeneous ones. What you see here is, so a photograph of terraced rice paddies. Rice paddies are classical case for heterogeneous environments. And the main message is that the distribution of biological populations is in many cases determined by heterogeneity. And this is actually something which biologists have noticed only recently. Here you see a statement by a very important population dynamicist, Peter. He said that in the last 2 decades it has become increasingly clear that the spatial dimension, and in particular the interplay between an environmental heterogeneity and individual movement, is an extremely important aspect of ecological dynamics. So basically, how is ecological dynamics modeled? Typically, if you have a vector of, say you have n interacting species, you collect their densities in a vector u, and basically you assume that u satisfies a reaction diffusion equation, reaction diffusion system, where the reaction part is accumulated in this function f, and you have to think of like birth and death processes or something like that. And then you have, of course, diffusion, which is basically the tendency of species to move into lower populated areas. It is typically assumed that diffusion is covered by a Fick-type law, which basically means that the flux vector is given by the product of a diffusion matrix and the gradient of the species, of the densities of the species. And the minus sign here just accounts for the fact that motion is always towards the lower populated regions. Classical application, and of course what is heterogeneity? It just means that all the parameter functions, f and t, for example, may very well depend on the position coordinate. This looks like a triviality, but it actually changes the mathematics to a large extent. Classical application is a so-called predator-prey system. Assume you have, say, one species of prey, and denote its concentration by U, and assume you have one species of predator, denote its concentration by V, then the classical model of interaction is this one. What does it mean? Well, basically you assume that both species diffuse with different diffusion coefficients. You assume that prey basically grows, well, it grows logistically due to the fact that if you have too much prey, they can sort of destroy their own nutrition. So this is this term here. And then, of course, there is interaction of predators and prey. And the interaction of predators and prey, of course, makes the prey species diminish. And it makes the predator species grow. And here in the modeling, you see clearly that without prey, the predators couldn't survive. They would die out. And, well, again, you have a lot of constants or parameter functions in these equations, like the diffusivities and these rate constants here, or rate functions here. And in many cases, they are decisively dependent on the position coordinate. Well, classical example, here you see again these terraced rice paddies. Well, of course, I mean, they are completely three-dimensional. There is flow of water, which is directional, so you can think of that the propagation of species in these terraced rice paddies is really controlled by heterogeneity. It's actually one of the classical examples of the biologists. Well, actually, people have used heterogeneity for a long time. It's well known that if you plant crops, you should not do what is called monoculture. You should just split the crops as you see here and here, and use heterogeneity in order to avoid unpleasant effects of species development. Well, here you see a photograph of an African savanna. An African savanna is, of course, a classical example for predator-prey models, where you have lots of predators in Africa, lions, eagles, leopards, and so on. You have, of course, prey like antelopes and some different, you have interactions, as you see here. Another important application of predator-prey models is the modeling of lagoons in urban environments. So here you see, for example, the Lagoa Rio de Freitas in Rio de Janeiro, a very big lagoon actually. And it turns out that the well-being, the health of the lagoon is to a large extent covered by the interaction of various species of plankton with nutrients and oxygen. And people now have written predator-prey models in order to describe the ecological dynamics of lagoons and study pattern formation and so on. Here you see the famous Corcovado in Rio, and then you can see about where this lagoon is. So actually this lagoon is in a very urbanized environment, and you can think of the fact that the well-being of this lagoon is very important for the ecological well-being of the city itself. Okay, change subject. Let me say a few words on optimal mass transportation and the so-called Montgomery equation. Well, what you see here is two construction sites. And on each of these construction sites, you see piles of construction material. And you can think of that this construction material has to go into certain holes. In French, you would say doublet for the pile, you would say remblai for the hole. And actually, you can think of the fact that it is very important how you transport this material from the doublet into the remblai. Why is it very important? Well, transportation, first of all, costs money. In this case, actually, it also costs manual labor, right? I mean, it's tedious, right? So it's an interesting question, and it's actually an important question to figure out how this transportation is done in an optimal way. And actually, this was formulated as a mathematical theory originally by the French civil engineer Gaspard Monge, and then it was actually worked out by the Nobel Prize winning mathematician Kantorovich. And now it actually goes under the name of Monge-Kantorovich mass transportation theory. Now, what is the basic mathematical problem? The basic problem is that you have a mass density, which is the doublet mass density, so the pile, the density of the pile. And you have a remblai mass density. And somehow the doublet has to go into the remblai. And it should be done in an optimal way. And when you write down a cost function now, which is quadratic in some sense, then you can prove that the optimal transportation is actually done by the gradient of a convex function. And this convex function V satisfies this very complicated fully non-linear elliptic equation, which is called the Monge-Ampere equation. And there is really very, very high-level mathematics involved with this Monge-Ampere equation. There is the study of existence of solutions, of regularity of solutions, which by now is, particularly due to the work of Luis Caffarelli, almost on the level of what we can say about the linear elliptic equation. And there is many applications of Monge-Kantorovich optimal mass transportation. For example, as I already said, optimal transportation of construction material. And this was really what the theory was made for. But also there is branching and irrigation flow networks. Think of river branching, leaf vessel branching, branching of trees or arterial systems in the human body. Where basically always the idea is to distribute a certain density of, say, fluids, of nutrients and so on into a certain volume or into a certain surface. Other applications are now in urban planning, like optimal distribution of residential and service areas. Or, interestingly enough, these techniques show up in fluid dynamical models in weather prediction. It's called then the quasi-geostrophic flow equations. Now, a typical application, what you see here is the branching of a riverbed. So you see that the transportation trajectories can have a very complicated geometry adapted to the topology of the ground. Again, you can formulate this as a motion autonomic transportation problem. So I think of lotus leaves. Basically, here the problem is of optimally distributing nutrient into the surface of the leaves. And the branch and the design of the vessels which nature did for the lotus leaf is for sure quite an optimal solution of the Markowich problem. Well, you see, here it didn't work out so well for other reasons, but these are there. Here you see, well, again, what is the problem in tree branching? The problem there is to sort of fill out a volume in an optimal way. Urban planning. Well, if you look at some cities of this world, you see, well, you don't really have a feeling that there's a lot of optimality issues entering into the planning. You see, if I'm an engineer, there's absolutely no planning. I can guarantee you that in some cities of the world, there is more planning for the cemeteries than for the living quarters. Okay, how much do I have? 5 minutes? I think I have 5 minutes. Wave motions. Let me say a few words about wave motions. Well, waves are all around us, and actually the workshop which Boltzmann is organizing at the IMS is focused on quantistic wave motion. So this is the macroscopic world, but there is, the microscopic world, but there is of course also macroscopic wave motion. For example, what you see here is an ocean wave hitting a beach. And human beings, scientists have been preoccupied with the modeling of waves for a very long time. Well, there is of course the linear wave equation, which most of you will probably know, which describes, in a one-dimensional case, the motion of a chord. For example, think of a chord of a guitar. Okay, that would be the one-dimensional version. The two-dimensional motion of a membrane. The three-dimensional version motion of an elastic body. Linear wave equation. Well, here is the Schrödinger equation, which models the essentially microscopic quantistic wave motion, which is what we are concerned now with in the workshop on Bose-Einstein condensation, actually with a nonlinear version of this equation. And then, of course, there is water waves that we are all interested in, and the basic model for water waves is the Corteweg-de-Vries equation, modeling shallow water waves in a one-dimensional channel. And there is two-dimensional versions of this modeling two-dimensional waves. And, well, you see that waves have interested artists, or even the Zen Buddhist artists, and they model, well, they actually formed circular waves here, and they were very worried about their interaction, and they were also worried about their interaction with the plane waves. I mean, it's very good from the artistic point of view, but the mathematics of wave interaction is, of course, much more complicated than what you see here. Well, here's an interesting picture. What you see is the breaking of a wave, the breaking of a water wave which hits a beach. Now, in mathematical terms, this is a very complicated phenomenon which basically leads to the idea of multivaluedness of solutions of wave equations, something which has been investigated in the last 5 years or so. A very complicated phenomenon. When here you see interaction of waves, you see a transversal wave, which is, or actually could be a circular wave, is not really clear, could be generated by the motion of this ship, but then you see a plane wave in the orthogonal direction, probably generated by wind, and of course the interaction is highly complicated. Here you see again an artist's interpretation of waves. This is the floor of a huge square in Lisbon. Of course, the Portuguese seafarers have been worried highly about waves for many centuries. Yeah, I think I stop here. Thank you very much for your attention.
Maybe a very naive question. Now,
I might give you an advance.
you talk about, say, computer matrix or animations from Vienna, but how much do you care about, say, the waterfalls of the movies and animations actually outweighing the physical laws?
Actually, they care about this very little. I mean, all they want is to get out something which looks good to the eye. And it just turns out that some of these methods can be used in a very fast way. And as you know, Hollywood has more computational power than I think Los Alamos and all the other defense labs in the US combined, so they can do it. I mean, they care about the physics only to the extent that it has to look good to the eye. But really some of these methods are very fast, and they can do it. I mean, it's in, some of them are in a primitive way, of course, in the Sonic console, which I find very fascinating.
I still wonder, what's in front of you?
Okay, that's a complicated question. This is a piece of it's actually a light installation done by a very famous Austrian artist. It's something that hangs on the wall. Okay, it's a very complicated system of mirrors inside with a light tube. Yeah? And the system of mirrors is made in such a way that you have the impression that it focuses. It's really very clever.
I do have a question. You show us a picture of the same that all those waves.
Yes.
Yeah. I suppose I suppose they just constructed, right? I mean, they have this gravel on
Exactly. Then they go.
yeah. So they said they worry about interaction in the boundary, but where I mean.
Well, in mathematical terms,
They just do it. I mean.
they just do it. Exactly. They don't worry about the interaction. I mean, this is actually what I meant. I mean, the reality is much more complicated.
Yeah, like if you say try to use a model for the movement of this wave, right? This is wave, circular waves are propagating and so on.
Exactly. And the plane wave.
And what happens at the boundary is very complicated.
Exactly. But I find it very fascinating that waves are something which enters the mind of the Zen art.
Yeah.
It is regarding free boundary problem. Actually, you gave the example of the membrane clamped over the stone, right? So, what is the free boundary over there? It is interface between the membrane and the stone, or?
No, the free boundary is technically defined as the boundary of the region where the membrane touches the stone. Okay, so if you, in a simplified way, if you think of a sphere as a stone and you put the membrane over it, then the free boundary will just be a circle.
Okay. Wherever it touches, it is called free boundary.
Sorry?
Wherever the membrane touches, it is called free boundary.
Exactly. And the main issue in analyzing free boundary problems is proving the regularity, that means differentiability of the free boundary. That's the main issue. It's really very hard. You have a geometric aspect on top of the analytical one.
I think the picture, check a picture is Curvature is the Guangxi curvature. Wrong.
Yeah. Weights already, Weights already told, but he didn't tell me how you spell it. Thank you. Maybe you can tell me after what the right thing is.
No more questions? Well, it's a very fascinating lecture. Well, it shows how the world is well complicated. right? or how much PPE can do for work. Understandable. Okay, please join me in